Happy holidays and welcome to a special episode of Adam Alonzi's podcast. Tonight we will be discussing breast cancer, breast reconstruction, and bioprinting with Laura Bosworth. Hello, Laura.
Hello, Adam. How are you?
Wonderful. Pleasure to have you on in this festive season.
It is fantastic to be here with you.
I stumbled upon some of your videos months ago and was intrigued by your company because at the time I was researching bioprinting. Now, can you tell us a bit about TeVido?
Yes.
Pronounce it for me.
TeVido. The name, just a little history, comes from the combination of two Spanish words. The word for tissue, which is tejido with a J, and the word for life, vida. So I replaced the J with a V, and voila, TeVido. But what at TeVido we're doing is we're using 3D bioprinters and living cells that we collect directly from patients to create reconstruction products. Really a broad platform, can address a great deal of needs in reconstructive surgery, but our first target is for breast cancer survivors who have had a mastectomy, and specifically to rebuild the nipple for those women who no longer have them.
I think we can all get behind that effort. Everyone likes helping others, and most everyone likes nipples.
Turns out men and women both like nipples, so it's a fantastic party conversation.
I know, I had no idea women liked them.
Yep.
It's a brand new discovery. What exactly got you into this field?
Well, it's a bit of an unusual story, circuitous, I might say. I am a former Fortune 50 executive, and I had the opportunity to leave corporate America a few years back, and I started working with entrepreneurs. And at the same time, I went to my former alma mater and joined the advisory board for the College of Engineering, and they asked me to help them with entrepreneurial efforts and innovation. And to make a long story short, as part of that, I told the dean, well, why don't you just introduce me to some of the cool work that you're doing in the engineering school, and my job as an advisor is to help. So I will mentor you, I'll do whatever is necessary. And they had some fantastic work that was going on there, one of which was Tom Boland, who is actually considered the grandfather of bioprinting. He's the one 10-ish, maybe 15 years ago, really invented the first use of a printer and printing cells. And the more I spent time learning about what you could do with this idea, the more I just was drawn to it and felt like you don't accidentally stumble across these things. You come across these things for a reason. And so, I went to Tom and to the dean and I said, I think we have to spin out a company and see what we can do. It's high risk. It's a long time to market, but if we don't start now, it's not going to happen. And that's kind of how it went.
Now, as anyone with a 3D printer knows, there are initially some challenges to printing even simple objects, and especially when you're inexperienced, but there are considerably more challenges to making living tissue, or making whole organs.
Yeah, there's probably a lot of things we could talk about, but one of the things is just to think about the scale and the size that you're working with. We're working with cells, living cells. Generally, depending on which cells you're working with, they're on the order of 10 microns, 20, 50 microns. So these are very, very tiny. And then cells are living organisms, and they have a very specific environment that is required to keep them alive. So just like, we have to have the proper percent of oxygen in the air, otherwise we don't make it. They too need to be fed oxygen as well as nutrients to stay alive. And so the ability to work at that size with the proper nutrients and to go kind of through a mechanical piece of equipment and still have the cells alive on the other side, and at the right temperatures and in the right environment, and then do what you want them to do is quite challenging. And so the bioprinter adds a complexity to that biologists have been working with for quite some time. So it's hard to know which is harder, just the biology part or the bioprinter. They're both complicated.
Right. You don't want to apply too much heat when you're shooting the cells out because that's not good for life.
That's exactly right.
And you want to get your scaffolding right because you need to get the cells to differentiate ever so precisely.
That's exactly right. You need them to do what you want them to do and potentially become what you want them to become. And so the environment has to be very, very carefully set to induce those mechanisms.
And we can throw out a bit of vocabulary here that relates to what you're doing. Allografts.
Allografts being typically in humans. That means you're using human cells, but you're not using your own human cells. You're using, a source, a safe source. Autologous, that's what we're working with. Autologous means that you're using your own cells. And then, of course, the other one, is xenografts, with an X, and that means you're using other animals, perhaps porcine or bovine, or like we like to say, pigs and cows. And all of those are used in, products, medical products, in human use.
But there are issues with xenografts, and there are even issues with some allografts.
Right. So one of the things that we look at quite a bit from the allografts are there's some really interesting skin tissue products. In fact, I want to say the first FDA-approved tissue-engineered product was an allograft, a dermagraft. And dermagraft is used, it's really a skin substitute. And the thing about those is although they have skin cells and they're live and they have a lot of the components, they don't really have vasculature, which is sort of your blood structure, your capillaries and things like that. They don't have that. And what you find is that they kind of graft, in other words, reconnect, but they don't fully. In some cases, they just create a very, very sophisticated bandage that has a very human-like environment. But they don't necessarily graft as well as, if the surgeon went in and took a piece of your rump and moved it over to where your wound is. The problem, though, with doing skin grafts is now you also have a wound on your rump. So in some cases, that's not very viable. Now, in the case of skin, because it's a very surface thing, there's not a lot of issues with rejection. But allografts, so another example of an allograft is organ transplants. So when people, need a liver transplant, they have to get that from somebody, unfortunately, who's probably just passed away, and they have to be on immune rejection drugs for the rest of their life because that's not your own cells. And so for us, we're working with autologous. We feel that the immune response, the rejection response, all of that should be extremely low risk. We think it's very unlikely that we'll have those sort of issues, and that's one of the reasons we're using autologous cells.
Really, it sounds like the only viable option, the most viable.
I think it is in a kind of this breast reconstruction space. It seems that the trade-off, the side effects of using immune response drugs, the risks associated with that probably don't outweigh the benefits of reconstructive improvements. So yeah, I just am not sure that an allograft in that scenario will work successfully if it's a permanent one.
And another word that I can see, but I am not positive about its pronunciation, Cellatier, your patented process.
Yes, Cellatier. So we have we have several pending patents. We have an exclusive license with the University of Texas, El Paso, and really focused on, using the printers, but also what the graft itself as a product is. And so, of course, the printing of the specific cells is some of the capability, but we're also looking at creating vasculature within our graft. And so as we talked about, the dermografts and things like that don't have that. And if you have a very, very thin graft, less than a millimeter, your own body will create capillaries that grow into that graft. And so then the capillaries provide the blood and can keep it alive. But when you start getting much bigger than a millimeter, the ability to keep all the cells alive long enough for your body to graft is a problem. And so that's some of what our technology has the ability to do. And we're using, a variety of techniques that we don't like to talk in too much detail about what those are. As you can imagine, the secret sauce is kind of special.
Of course. And no one would expect secrets to be divulged here, of all places.
No, of course.
Vasculature and getting the growth factors just right is one of those major hurdles. Have you guys been using any computational techniques to figure that out?
We have not been doing that. That doesn't mean that we won't. That's a possibility. But at this point in time, we have not been doing any of that.
Well, if it works. If it's not broken, don't fix it.
Right.
Of course. So it's been sort of experimental trial and error.
Yeah. We're still in relatively early stages, and so we are trying different geometries, different combinations of cells, the different bioinks, if you will, which is really kind of the environment that I talked about how you keep it alive, is what's that formula for your bioink. And that ink tends to differ from cell type to cell type, and we're putting multiple cells together. So, the recipe is somewhat sophisticated, and just trying to get all the flavors to blend together is a bit of a trial and error.
That's what makes biology so beautiful compared to, say, chemistry. Chemistry, you have one compound, you have another compound, they're going to react. Biology, you have this vast array of molecules, this great symphony. It's like playing a banjo versus conducting an orchestra.
Right.
And you are Schubert in this
and you do
great
have to
endeavor.
Count on the individual violinist to do what that violinist does best. So in our case, we have certain cell types and they have a role. And what we have to do is create that environment that they can play that role. They can, fiddle if they need to fiddle, or play Chopin if they need to play Chopin.
And breast cancer is becoming, it's a fairly popular topic, and has been for a number of years, but most of the people I've spoken to who have gotten into it have personal reasons for developing the interest.
Yeah, and what you'll find is that in any group of people that I go to speak to, you really can't go to a group of people and not find somebody who's had either they themselves or a loved one or a friend who's been impacted by breast cancer. In the Western world, 1 in 8 women will get breast cancer in her lifetime. It's, the most common cancer for women. And so, unfortunately, that means it's very pervasive and it's touched everyone. You might be asking in a subtle way whether I personally have that experience. I do not. I have been diagnosed with melanoma, which of course we're working with skin, and the reconstructive space has the potential for, rebuilding scars and tissue deficits from things like melanoma or soft tissue sarcoma. So there is a lot of application. broadly in the cancer space in Reconstruction. But other than knowing quite a bit of people who've been impacted by breast cancer, I am, knock on wood, I'm not yet one of the one in 8.
Well, no, it was subtly asking if you knew anyone.
Of course, you can't not know somebody.
Close to. I'm not sure if... Oh, wait, I do. No. Wait.
Probably if you talked about it, you'd be surprised how many people will come up to you that you don't realize, right? Just even friends that maybe their aunt or their grandma or somebody like that has been.
In the extended network.
Yeah. Now, so one of the things, though, that I do want to talk about is that, 30 years ago, the 5-year survival rate for breast cancer was about 75%. And as you mentioned, you hear about breast cancer a lot. The Komen Foundation, there's a lot of very public activity. And a lot of that research has really had a huge, huge impact. So today, the 5-year survival rate is 99%. And that's pretty fantastic. And what it means is that women are getting diagnosed at a much earlier stage, so their survival is longer. They're getting diagnosed younger. And even preventative mastectomies are on the rise, right? So they know about what genes, so you don't even have to have it. You don't even have to detect it yet. You can know that you are predisposed with certain genes are something like an 80% likelihood that you'll get breast cancer. So these preventative measures are being taken. What that means, though, is these are really young, dynamic women with a huge part of their life left. And the loss of a breast it's an amputation. People don't think about it that way, but it can be really devastating emotionally. And so reconstruction is becoming more and more important. And so things like this, it might seem superficial. Why do you need a nipple? You're alive. It's like, yes, but I'm going to be alive for 35, 45, 55 more years. And I have to look in the mirror every day and want to be able to feel good. And so that's really what we're all about.
Now, if someone had the BRCA gene variants that predispose them to breast cancer, and they have an autologous implant, I suppose the tissue would still be susceptible to developing it.
Yeah, it's a great question. And what we are intending to do, so there's a couple of things, is that our intention is not to use breast tissue to rebuild the nipple, largely for that reason, right, is who knows? Who knows where these cancer cells might live? So we would be taking cells from the tummy or the thigh, perhaps the back, somewhere else, which is not in that area. The other thing to know is that for decades, one of the techniques for breast reconstruction has been, they call it autologous flap transplants. And so effectively, and this is to recreate the breast mound. So instead of an implant, they essentially cut out a portion of your tummy or your back or even your thigh, and then they move that. It's a large piece of tissue. And they move that over into the breast area, and it's large enough that they reconnect the veins, to another vein that you have, so that it can be vascularized. And so, that's been going on for decades. And what we're talking about doing is potentially just using a much smaller sample of cells from these locations where they've already been, using them for breast cancer patients. So, we've been very deliberate in thinking about how do we do that, and how do we, we don't want to increase the risk of, any future breast cancer showing up with these patients. So we're trying to follow all the learnings that are out there already.
Maybe genetically modify the autologous cells or those BRCA variants.
Yeah, that's an interesting idea. I think that would certainly not be in the first round. But, we've got a lot of years. There's going to be a lot of years of this out there. And at some point,
yeah.
how you bring in the nerves and recreate feelings and this field of regenerative medicine, we're just at the beginning, the very, very beginning, taking baby steps. And so the possibilities of what can be done is pretty phenomenal.
I can imagine some people thinking it is superficial, but that's because what they don't understand is you're also doing fundamental research that will have long-ranging applications go on, and I assume that this is not where your company will begin and end. There will be many other things on the horizon, and the more we learn about bioprinting, the more we can do, the more we can help everyone.
Exactly. For us, in sort of the short term, which for a biotech company is probably 5 to 10 years, as opposed to, an app. Short term is like the next 6 months or 3. We are likely to stay quite focused on using fat cells and skin cells, right? That will be our biology expertise that we have, but we also feel that we will develop quite a bit of capability in the vascularization. And that component could very well be used by other researchers and other companies that are developing livers and kidneys and, brains, who knows what else they might be working on. And so we think that's quite applicable. So hard to know exactly where it would go. Our thinking would be more of, from a business perspective, licensing out that component of the technology, and then we ourselves stay in kind of the expertise of reconstructive and even cosmetic surgery.
Sure, and none of those are trivial problems. They're very difficult, and they're going to take time to solve.
Right. And one of the things, Adam, that's interesting is that if we talk a little bit about the nipple, what we know is that the average kind of nipple size of the projection is, say, a centimeter, maybe, could be a centimeter and a half, as far as the projection. And in the field of tissue engineering, that's actually in the field of tissue engineering, that's really big, right? Because a centimeter, if you can only vascularize about a millimeter at a time, that's big. But compared to needing to build, a kidney or a liver or a heart, it's relatively small. And so one of the great things technologically about the problem we're working on is that it is quite achievable. That was what we had to think about, is where is there a need, an unmet medical need that's relatively small tissue? And so we think the nipple is the right one.
It seems like a good bet to me. It seems like a good idea to start with something that can be achieved in a relatively brief period of time, and then move forward. Right. And I think that's precisely what breast cancer survivors want to hear, and precisely what your investors want to hear.
Well, that's what we're hoping for.
All right, and the third question. Your tips for aspiring entrepreneurs and biotechnologists.
Well, I worked quite a bit with entrepreneurs before going down this path myself, and I think there's, one of the things when I'm coaching people is always to say, you need to be thinking about, come up with your plan. Like, this is how long I think it's going to take. It's going to take me 2 years to write this app and launch it and get my customers and, yada, yada, yada. And then double everything. And decide for yourself that if it takes double the time and double the cost, is it something you can do? Because, when you're an entrepreneur, you're usually not making much money. You're maybe spending a lot of your own money. And there's a lot of people who cannot do that for very long. And so if you can only do that for 6 months, then you're probably not ready yet. So there's all you have to do about your ability to handle that type of risk. And so that's one of the things. I think the other thing, too, is you have to listen to the advice that people give you and recognize that most of the advice is going to disagree with each other, right? You know, one person on the left says this, person on the right says this, you know, somebody in the middle says a different thing, and then but you're still the one responsible for the path. I find a lot of people, certainly when they talk to me, they want me to tell them, well, what's the right answer? And the answer is, well, probably nobody knows yet, otherwise it would have been done. And so you are the expert, and so your path needs to be is the most educated path that you can be on at this time. And so, you know, I find that's another thing that early entrepreneurs seem to get very frustrated that they get mixed advice. And so I think you just have to work through that. Now, biotech. Oh my gosh. Don't just double the amount of time, you know, multiply it by 10. And I do often ask myself, you know, what was I thinking? This is such a long path. And in general, a lot of investors, a lot of people, they're like, boy, we love what you're doing. This is so fantastic. You know, come back to us when you're ready to enter clinical trials. And it can be difficult because you're thinking, okay, but so that's like $5 million from now. In, you know, 2 years, I don't quite have that in my back pocket. And so I think the biotech field can certainly be a very, very long one, and especially if you're trying to be innovative and groundbreaking. And thank goodness for federal agencies, because really that's how most companies like mine manage to get through that gap. And we are funded by the National Science Foundation and the National Cancer Institute, small grant from the Livestrong Foundation. And, you know, without those, kind of what's going to get you past that $5 million before investors start saying they really want to jump on the bandwagon, that's the kind of stuff we need.
That is quite a counterpoint, because so far the majority of my guests have cursed federal agencies and all forms of regulation. So yay for that diversity of experiences and opinions.
In fact, I think I just saw on Facebook today that's the anniversary of when the National Cancer Institute got their mission some decades ago, and I thought, oh, what a blessing for companies like mine.